All right. I will begin with a word of prayer. Heavenly Father, we thank you again for this day and your many blessings, and I just pray that you'd be glorified in what we do and that we all understand a little bit more about inner product spaces and how they work, Lord. In my prayer, Lord Jesus. Amen. All right, so here we go. We will be covering the little remaining sliver of section 6.1 and 6.2 today. So basically, we're in 6.2. Section 6.2, which is basically on the Graham-Schmidt algorithm and the orthogonal complement. All right. So first order of business, what do we mean by orthogonal? So here's the definition. If V with Langle-Rangle is an inner product space and S is a subset of V such that x comma y in S implies the inner product of x and y is equal to 0, then S is orthogonal. All right. S is orthogonal. And in this situation, we could also use the language, and we will use the language as it's convenient to us, that this we can also read as x is perpendicular to y. All right, so x is perpendicular to y. Another way to say this is an orthogonal set is a set where every pair of vectors is orthogonal. All right. What's a unit vector? So a unit vector x in S, not S, but V rather, has the norm of x, which how do we define that? We define that to be the square root of the inner product of x with x, right? This is equal to 1. Okay. Any vector can be written as the product of a unit vector and its magnitude, right? Notice that if we have x, we can rewrite it as x over as 1 over the norm of x times x over the norm of x, and it's a simple matter to show that if we define x hat to be x over norm of x, theorem, it's a tiny theorem, but the length of x hat is equal to 1, right? This is not in the textbook, but I think it's worth repeating. Now, I said all this, but it's not true. Why? What's the dirty lie? Fine print I have not attached yet. What do we must assume in order to calculate the unit vector? What's that? Non-zero, right. For x not equal to 0, any non-zero vector we can write as the product. So notice that this gives us that. Oh man, what did I just do? That's nonsense. Look at that. Good grief. Come on. You guys would have complained. You were formulating your complaint. I just beat you to it. There it is. So any vector can be written as the magnitude of x times its direction, which is x hat, right? Any vector can be expressed as a magnitude times the direction. This is true even for polynomial vector spaces or whatever. This is like generally a truth of inner product spaces, right? Hopefully you saw that in Calc 3, right? Okay, so that's part of our definition. What else? If S is an orthogonal set of unit vectors, then S is orthonormal. Orthonormal means orthogonal and normal at the same time, all right? So let me make a remark here that we'll use over and over again. If you have beta equal to V1, V2, all the way out to Vn here, right? A basis for V, and the inner product of Vi and Vj is Kronecker delta Ij, all right, then beta is orthonormal, and orthonormal so what would an orthonormal basis mean? I mean, the book defines it at the start of section 6.2, but it is simply a basis, which is also orthonormal. Okay, yeah, there you go. And this condition does that for you, right? Because this is equal to, how does this work? See how this works? 1 if I is equal to j, 0 if I is not equal to j, right? So from I not equal to j, we have orthogonality. In the case I equals to j, what do you get? Right? But it's also equal to the norm of v sub I squared by the induced norm that we find last time, right? Therefore, it's a unit vector. Every vector in there is a unit vector. So a nice formula for expressing orthonormality is simply this lovely little formula right here. What would the formula be for orthogonality? For S orthogonal, you know, and S equals to V1, V2, and so forth, right? So if it's like that, then we have the following. The inner product of Vi and Vj is equal to the norm of Vi squared times Kronecker delta Ij. And the proof is nearly the same as I just told you. If I and j are distinct by assumption, their dot product is 0. I mean, their inner product is 0. Excuse me, my dot product was showing. And then if it's equal, well, the Vi with Vi, the inner product of Vi with I is just the length of Vi squared. And so this formula, of course, matches both of those. So there it is. As a formula, that's orthogonal. As a formula, that's orthonormal. All right? Now, so example 1, remember this H space that we had, which was what, like, you know, F mapping from 0, 1 to the complexes, right? Such that F continuous. In this context, we can look at Fn of t equal to e to the int. Now that is cosine nt plus I sine of nt by Euler's identity, right? And so we can calculate the inner product of, say, Fn and Fm, and that is by definition 1 over 2 pi, the integral from 0 to 2 pi of what was it? Well, e to the int times e to the what? What was the rule? We do the function times its complex conjugate in this context, right? What's the complex conjugate of e to the int? It's simply e to the minus int if you look at it. All right? And here I'm going to assume m is not equal to n to start with. All right? Now if I have that, imaginary exponentials obey the law of exponents, so you get e to the 2 pi e to the I times n minus m times t dt. And indeed, calculus works just like you'd hope. So this is actually 1 over 2 pi n minus m times I. e to the I n minus mt, evaluate that thing from 0 to 2 pi. But the cool thing about this is you're going to get 1 over 2 pi n minus m times I e to the, 2 pi n minus m times I minus 1. But what is e to the 2 pi, any integer multiple of pi? Any even integer multiple of pi? When you feed it to sine and cosine, what happens? Right? If you plug in a 2 pi multiple into here, that's 0. I mean, that's 1, right? And that's 0. So we get 1 minus 1, which is 0. All right? On the flip side, what happens if you look at like fn with fn? So we've got that 1 over 2 pi from the definition that we made. And now you'll maybe understand why the 1 over 2 pi is there. Integral from 0 to 2 pi, e to the int, e to the minus int dt. And what happens? Well, those cancel out, right? So these cancel. You just have integral of dt. So we get 2 pi over 2 pi, also known as 1. So this calculation shows you that apparently the subset e to the int, such that n equals 1 to infinity, is an orthonormal subset of H. All right? We will shortly argue that orthonormality gives us linear independence. Yeah. I didn't close my parentheses. That one? Unsettling, isn't it? I'm not sure if that's going to bother you or Josh more. Well, you got to think of it going. Oh, wait a minute, no. Like that. It wraps around. Okay, moving on. So, other examples. So before I got interrupted with an important question, I just messed with you. This is a linearly independent subset of H. How many vectors in there? Infinite. So what does that say about H? It's infinite dimensional, right? So, okay. In any event, here's some easier examples. If you look at E1 through En in Fn with the usual dot product, if you look at the matrix units, right, with I like to use A and B for this one. Right? If you look at, well, anyway, so these both are orthonormal bases. These are orthonormal bases for column vectors and the matrix units. So the matrix units all have length 1 and they're perpendicular, right? So you can prove it. Unless, just kind of an odd example, but just to throw in something a little bit different. If we do 1 over the square root of 5, 1, 2, 1 over the square root of 5, something is orthonormal basis for R2, you guys fill in the blanks here. What would you put? I got to vote for a 2, -1. Yeah, that is one of 2 possible correct answers. Right? The other answer is? -2, -1. Yeah. See, basically, geometrically, you can either rotate 90 degrees this way or 90 degrees that way from your original vector. Okay, so theorem. Let V equal to, well, let V comma that be an inner product space and S a set of vectors orthogonal, an orthogonal subset of V. All right, consisting of non-zero vectors, then if y is in the span of S, then y is equal to a sum I equals 1 to k of the inner product of y with vi divided by the length of vi squared times vi. All right. So this is basically telling us how to find the components with respect to an orthogonal span. And the proof of this is very simple. You just simply suppose you have something in the span, and then you take the inner product with it. All right, so like proof goes like this. Let's let y equals to the sum I equals 1 to k of ci vi. All right? Good so far? Our goal, our mission, should you choose to accept it, is to show that ci must be equal to what's in parentheses here. Once we do that, we're done. Okay? So consider the inner product of y with vi. Not vi, but we'll do vj. All right? So that's equal to the inner product of the sum I equals 1 to k of ci vi with vj. Right? But by properties of the inner product, I can pull out the summation, and I can pull out the constants y. Because I'm in the first slot, right? There's no conjugate linearity here. And so we're just left with the inner product of vi with vj. All right? But remember what I said, orthogonality means this is the inner product, the length of vi squared times the Kronecker delta ij. That's orthogonality. So the Kronecker delta is the natural enemy of the finite sum. The only thing this is non-zero for is the fixed but arbitrary j, which just leaves me with cj times the inner product of vj squared. So therefore, cj is equal to the inner product of y with vj divided by the length of vj squared. Now why can I divide by the length of vj squared? Like, why is that legitimate? What if the scalar is 0? Yeah?
Defined to be non-zero.
But that's not the vector, that's the length of the vector. You're right, but
Isn't one of the axioms that for
yeah.
not zero, that's positive?
Right. Well, for for us it was a theorem, but yeah, if we have the norm of x equals to 0, if and only if x equals to 0.
Oh, right.
This was a consequence, the derived consequence for the induced norm for us. But there you go, that's the theorem. What happens here, like a corollary, obvious corollary, let me write it down before I move on. Corollary, right? If S orthonormal, then y equals what? Excuse me. Same thing, but what?
You don't have to divide by length.
Very good. So we just do, inner product with y and vi times vi. And there you go. That's the corollary. For an orthonormal basis, the components are even, now I'm saying it's a basis now, but I mean, this has an obvious application to the problem of a basis, right? If S is a linearly independent spanning set for the whole vector space, and it's an orthonormal basis, then these would actually be the components of the coordinate vector of y with respect to that basis. In other words, we can calculate the coordinates with respect to an orthonormal basis simply by taking inner products, which is ever so much nicer than trying to invert a basis matrix and multiply, right? Or whatever else is involved for an abstract space. Okay, moving on. So corollary 2, a non-zero orthogonal set of vectors is linearly independent. Can you see why that's true? So this is corollary 1. Corollary 2, S orthogonal and non-zero implies S is linearly independent, right? Why is that true? What's the proof here? Basically just this. Think about y equals to 0. If I have a linear combination of the vectors equals to 0, the coefficients are given by 0 comma vj divided by the length of vj squared. But 0 comma vj is, by one of the axioms of the inner product, 0. Therefore, orthogonal non-zero implies linearly independent, because if we take a linear combination equal to 0, we get, it must be the trivial combination. So from the definition. So that's super nice. So question, see if you're tracking what I'm saying. Is a orthonormal set linearly independent? Is that necessarily the case? What do you think?
Yes, because they're all orthogonal.
Uh-huh.
Because the length of each one is 1.
Uh-huh.
And the only way that the length can be, or the only way that x can be 0 is the length of x is 0. That means because the length of them is all non-zero, they must all be non-zero.
Right, because the length of each vector is 1. It means all the vectors are non-zero. That's exactly right. So, indeed, orthonormal sets are linearly independent. This is the actual Graham-Schmidt algorithm. Here it is. Let V with inner product lingle-ringle be inner product space, and S. I'm going to put a sub n here. S sub n equals to W1 Wn be a subset of V. Well, let me say it this way. Be linearly independent subset of V. All right. define S prime equal to, and I'll put a sub n here, v1 dot 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 vn by v1 equals to w1 and vk equals to wk minus the sum j equals 1 to k minus 1 of the inner product of wk with vj divided by the length of vj squared all times vj for, and this was for 2 less than or equal to k less than or equal to n. What's the punchline? Then S sub n prime is orthogonal and the span of S is equal to the span of S prime. And I should be, I'll put n on here to emphasize that there is a n dependence to this claim. How are we going to prove a n dependent claim for all n, do you think? Induction sounds like a good choice. Is it true for n equals to 1? So the proof by induction on n. Let's see here. So first of all, it's clear that it's, you know, if we look at S1 is equal to what? It's the set containing W1, but that's equal to, by the algorithm, V1, right, which is equal to S1 prime. Clearly the span of these are equal. The theorem's true in this case, right? So suppose that S sub n minus 1 prime is orthogonal, and that the span of S sub n minus 1 prime is equal to the span of S sub n minus 1, right? So consider Vn equal to, and so we're gonna try to show that we'd like to look at the next order up, right? N minus 1, so let's look at n. So Vn should be equal to what? Wn minus the sum j equals 1 to n minus 1 of the inner product of a w sub w sub n with vj divided by the length of vj squared, all in the vj direction, right? So if this was equal to 0, we'd be in trouble, right? So the claim is that, well, let me just, no, we're fine. Well, let me just think about it this way. If this was equal to 0, then we wouldn't be able to get that the span of n, the span of this is equal to the span of that, right? Because you'd have at least one less linearly independent vectors in the set Sn prime, which we wouldn't be able to have the span as equal, right? So it's important to know that this is non-zero, because then that will give us, if we can prove that it's orthogonal, the set Sn prime, which is orthogonal with n vectors, and then it follows that if you have n non-zero orthogonal vectors, they're linearly independent, right? And then the span of Sn prime so constructed is clearly a subset of Sn, but it's a subset of Sn that has a spanning set that's as large as the spanning set for the Sn itself, which then follows the have equality of the spans. So this is really, this and the orthogonality are the two things we have to be checking. So to show that Vn is not equal to 0, suppose it's 0 and we'll find a contradiction. All right, so let's do that. So what happens if you put this equal to 0? What does that mean? That means that Wn, right, is equal to the sum of all this stuff, right? But what is all this stuff? I mean, numbers, right? These coefficients, whatever they are, it doesn't really matter. But notice what the j is ranging over. Where is it ranging? It's ranging from 1 to n minus 1, right? From 1 to n minus 1. That means that Wn is an element of the span of S sub n minus 1 prime. Because S sub n minus 1 prime is, to be clear, the span of these things, right? So, you know, I've built things from a linear combination of the v1 through vn minus 1. That is the span of S sub, that means this is in the span of S sub n minus 1 prime. But remember, by the induction hypothesis, this is equal to the span of what? S sub n minus 1, right? So what does that say? That says that Wn is an element of the span of Sn minus 1. Which means that Wn is a linear combination of W1 through Wn minus 1, right? That means that Sn, which is what? W1 through Wn, is linearly dependent. But what did we assume about Sn? We're assuming it's linearly independent. That is thus a contradiction. So therefore, Vn is not equal to 0. Vn is not equal to 0. That's half of the proof, right? It still remains to prove that Sn is orthogonal, right? We now know that Sn prime, we now know that Sn prime is a set of non-zero vectors by the induction hypothesis, right? It remains to show that they are orthogonal. See here. If you're wondering how I know they're all non-zero, it's because of the span of, it's this condition right here. If they were 0, that would spoil that. All right, so the proof that they're orthogonal is actually pretty simple. So let's do it. What'd I do? This is all your fault. It's her fault, isn't it? You can say yes. Say yes.
No.
Say yes.
Yes.
That's better. Is this teacher abuse? Like making you say things against your will? It's got to be some kind of abuse. See here, I don't know. It's definitely at least a medium-sized aggression. We're well past microaggressions here. Let's see here. Where was I? Oh, yes. So let us calculate Vn with Vi. All right, so that is using the formula, the Gram-Schmidt formula. That is literally Wn with Vi. And I'm going to just go ahead and pull out the sum using the properties of the inner product here. Sum j equals 1 to n minus 1. I've switched from k to n in my lecture here. It's really annoying. I don't know why I did that. I got k's in my notes. I got n's up here on the board. So if I slip and write a k up here, stop me. Vj divided by the length of Vj squared. Vj, all right. But what's the story? Remember how this goes? So, whoa, second. Oh, I didn't copy it down right. I'm sorry. I got to think through this, right? So that's just the coefficient I pulled out, right? But we still have the Vj. There's Vj on Vi here. This is what I get for skipping a step, you know? My bad. So the Vj from this with that Vi. All right. But remember, we are assuming by the induction hypothesis that these are orthogonal. So this is going to be the length of Vj squared times the Kronecker delta Ji, right? So what happens is this and that, they be canceling, and this simply becomes Wn Vi minus, well, Wn with, here I is fixed but arbitrary, so we keep the I, we lose the summation over J, and we just get Vi, which of course is 0, and that completes the proof. So therefore, we've shown that S sub n prime is a orthogonal set of non-zero vectors, right? Therefore, it forms a basis for the span. So this basically tells me that the Sn prime gives basis for the span of Sn. And I know that the span of Sn, this is n-dimensional, right? By assumption, we have n linearly independent vectors. We're forming the span. That's an n-dimensional subspace, right? This is another set of n vectors, which is linearly independent because it's non-zero and orthogonal. It's also clearly a subset of that span. Therefore, the span of Sn prime is equal to the span of Sn. And that completes the proof, okay? So this is the Gram-Schmidt algorithm, and there's a lovely derivation of the formula in part in the book. Like it actually derives like the starting point of it. Kind of a neat little calculation. I'd encourage you to look at it. Let me just show you a weird example. So let's see here, what example? Oh man, I erased my example numbers. We're on 5? Maybe? I'm going to call it example 5. It's example 5 in my notes. We're going with example 5. So if we look at, P2R with the inner product of f and g being the integral from -1 to 1 of, say, f of t, g of t. Let me not use t's. Let me just use x's here. Could not be weird. F of x, g of x, dx. So the book has like f of x and g of x in the inner product, and then it changes them to t in the integration. Don't read too much into that. It's just style. Now the book says the standard basis. So I don't use this notation. I don't use this language much, guys, but the book says the standard basis for P2 is beta, and they say that that's 1x and x squared, and I suppose that's a good enough choice. So the question is the standard basis for P2, is this actually an orthonormal basis? Is it even an orthogonal basis with respect to that inner product? Right? So let's find out, right? Like what's the inner product of 1 and 1? What's the inner product of x and x, right? What's the inner product of, 1 and x? what's the inner product of, oh, I don't know, x and x squared? You know, what's the inner product of x squared and x squared? Can you guys work these out? Shouldn't be hard, right? Integral minus 1 to 1 dx. Integral minus 1 to 1 of x squared dx. Integral minus 1 to 1 of x dx. Integral minus 1 to 1 x cubed dx. Integral minus 1 to 1 x to the fourth dx. Yeah?
Well, for 1 ends up being 2.
So we got we got a 2. We've got a 2/3. We've got a 0. We got a 0. Integral of an odd function of a symmetric interval, 0. Yeah. And this guy gives me 2/5. So they're not orthonormal. They're not normal, right? They're not unit vectors. And they're also not entirely, I mean, 1 and x are perpendicular, right? So if I want to find an orthogonal set that spans P2, I can definitely use 1 and x, right? So like the Gram-Schmidt algorithm doesn't do anything, pretty much, to start with, because you can just use 1 and x. Those are orthogonal. But so if we set W1 equals to 1, W2 equals to x, W3 equals to x squared in the algorithm, we're going to get V1 is 1, we're going to get V2 is x, and then V3, well, V3 we're going to have to think about. All right, so V3, I guess I'll do it over here, I got more room. V3 is what? It is going to be W3, which is x squared. I'll write it out symbolically. So we get W3 minus the inner product of W3 with 1 divided by the length of 1 squared times 1 minus W3 inner product with x divided by the length of x squared times x. So that is x squared minus, what's the inner product of x with 1? Oh, that's right, it was, excuse me, what's the inner product of x squared with 1? Did I not do that? Well, it's 2/3, right? You notice that this is equal to, isn't that funny? There's actually some kind of, if you think about this more, you can get a lot of mileage out of, like the sum of the degrees is the same, the inner product's the same, you know what I mean? Like the inner product, if I was working with x cubed, like x cubed in 1 would be the same as the inner product of x squared and x squared in this game. You know? So anyway, x squared with 1 also gives us, this is 2/3. And so we've got 2/3 divided by, well, 2 times 1. And
The 1 is the square root of 2.
but it's the length squared down there. Yeah. Oh, the length of 1 is the square root of 2. That is kind of messed up, isn't it? Yeah, I like that. Yeah, good point. So W3 with x is, again, x squared with x, which we know is 0. Yeah. So x and x squared are perpendicular in this world. So that just gives us 0. And so long story short, V3 is x squared minus 1/3. So Gram-Schmidt gives us V3 is x squared minus 1/3. And then this is not entirely obvious, but you can normalize these. And part of this won't be surprising. 1 over the square root of 2. And then I'll have to look. I don't feel like calculating it at the moment. But it turns out to be square root of 3 over 2 times x. And then square root of 5 over 8 times, well, 3x squared minus 1. So this right here is what I get from normalizing the orthogonal basis. How do you normalize a set of vectors? You simply take the vectors and divide each one respectively by its length, right? That gives you a unit vector in the same direction. This is a special example because it has a name. The These ones right here, this, and that, these are called Legendre polynomials. And they play a special role in mathematical physics and such. All right. Moving along. If I can get my eraser. So, what can we do with all this? If you've got a finite dimensional inner product space, what can you tell me? Right, that's right. Any basis can be orthonormalized. So that's essentially the next theorem, which is just what you said. So theorem, if V comma, is finite dimensional inner product space, then V has orthonormal basis beta, which let's say V1 through Vn, such that if x is an element of V, then x is equal to the sum, I equals 1 to n, of the inner product of x with Vi. And the proof of this theorem is literally just, if it's finite dimensional, take a basis, right? Take that basis, run the Gram-Schmidt algorithm on it. That gives you an orthogonal basis. Take that orthogonal basis of non-zero vectors, normalize each vector. That gives you an orthonormal basis. And then we had this result, I just erased it. That's it. That's the proof. So any finite dimensional inner product space can be given an orthonormal basis. And this has some very nice effects. So like here's a corollary to it. If we have a linear transformation from V to V, linear, then like the matrix of the linear transformation with respect to an orthonormal basis, it's super nice. Let us calculate it. How do we calculate the column of this with respect to the beta basis? Well, if we look at T of, V, let's say Vj, that would tell me about the jth column of the basis with respect to the basis, the beta basis, right? But this is a particular vector in V. As such, I can expand it according to that rule, right? So this is equal to the sum, I equals 1 to n of, well, here x is the T of Vj, right? Vi. But what does this tell me? This tells me that if I look at the jth column of the T beta beta matrix, using my notation, not the books, of course, and if I look at the ith component of that, what is it? Well, it's exactly T of Vj, comma Vi. So that's how I can calculate, like if you like Aij for the matrix. I simply take the inner product with the output of the basis. And that tells me the matrix with respect to an orthonormal basis. So these coefficients have special names. They are known as Fourier coefficients. So if you're calculating the components of a vector with respect to an orthonormal basis, they call these things Fourier coefficients in this special context, all right? So the next order of business, of course, is orthogonal complements, right? So let me define that for you. So definition. For S, a subset of V, an inner product space, right? And I think we need S non-empty. I'm not sure about that. I think it's non-empty, yeah. Well, S perp is equal to x and v such that the inner product of x with y is equal to 0 for all y in S. So this is read the perp of S. All right. So you can prove that the perp of S is in fact a subspace, right? And when I say you can prove, I mean that's probably one of your homework problems. So, but that's an easy homework problem. You'd like me to assign that one. So just, for a concluding example here, example 6, maybe example 7. We'll do 2 concluding examples just to get us started on this. What is the perp of 0? What is the perp of v? And if we have E3 is an element of R3, what's the perp of the E3 space? What do you think? Of course, here I'm talking about with respect to the standard dot product, right? So for these two, what do you think this is? The whole space, right? So inner product with 0 is 0 for every vector in V, right? Therefore, 0 perp is V. V perp, on the other hand, is saying that it's the vectors which are perpendicular to every single possible vector in V. And we had a cancellation property for the inner product, and that cancellation property would prove that this has to be 0, only 0. What do you guys think this is? I'll start you off. Span of what? E1, E2. There you go. So the perp to the z-axis is the xy plane. I very much enjoy the orthogonal complement theory and what we have to say about it next class, but unfortunately that's inaccurate because next class is a review for that pesky test that's coming up, right? We're done.